Hi everyone, welcome to the ACIGS December webinar. So I start sharing my screen. This is our December 2019 webinar from the Australasian chapter of the International Geosynthetics Society. So in our webinars, we have participants from South Africa to Australia and New Zealand and many Asian countries. That is the ACIGS or Australasian chapter range. Basically, we get memberships. So our 2020 membership campaign is on now, and we have started the campaign for 2020. Make sure you visit our website and become a member of ACIGS. The benefits of joining the ACIGS, as I've mentioned before, are subscriptions to the IGS newsletters and also the ASICS newsletters. You also get access to the online IGS mini lectures, free access to the two prestigious publications, Geosynthetics International and also Geotextiles and Geomembranes, and discounted rates for all our events, which are the seminars that we do. We are currently planning for a seminar in March 2020, and also the webinars, which we have a range of different topics that we will be talking about in our webinars in 2020. ACIGS.org or www.acigs.org is our website, and make sure you visit the website and go to the membership page and register for 2020 membership. Just a note that we record this webinar and also all the other webinars that we do. We record them, we upload them to our website on the resources page that you can see here, and you can access to those recordings after the webinars or after each of our presentations or seminars. Today's webinar sponsor in Australasian chapter is Fabtech. We thank Fabtech for the support, and we will have a short presentation by Fabtech at the end of the Tim Stark's presentation. A couple of notes. Please note that this webinar will be simultaneously broadcasted in Australia, Australasia, I should say, and the United States in collaboration with the Fabricated Geomembrane Institute, FGI. So we will be using two platforms, Zoom for the Australasian audience and GoToWebinar for the United States audience. This webinar, as I said, will be recorded and will be available on both ACIGS and FGI websites. If you have any questions during the webinar, please type them on the Zoom or GoToWebinar platform that you're on, and we will get to them at the end of the presentation. Today's presentation topic is fabrication, installation, testing of geomembranes by Professor Timothy Stark. Just a brief introduction of Tim Stark. He is a professor in the Department of Civil Engineering at the University of Illinois at Urbana-Champaign. Dr. Stark has been conducting interdisciplinary research on geosynthetics and in particular geomembranes for the last 25 years. This includes his research on the installation and long-term durability of geomembranes and geosynthetics in geoenvironmental and seepage applications. He is the technical director of the Fabricated Geomembrane Institute, FGI, which is an industry-sponsored research organization investigating the advantage of geomembranes for containment and seepage application. Here is a photo of Tim Stark when he was he visited us in Australia this year, actually in 2019 February, and I'm sure he had a good time in Australia, and that made him give us this presentation today. Thanks, Tim, and I stop share from my screen, and we get you to start your presentation. Thanks.
Thank you, CMAC. Good afternoon, Australia and New Zealand. It is a pleasure to chat with you again. I really enjoyed my visit in February this year, and great. Thank you, CMAC. Great. Thank you, CMAC. Good afternoon, Australia and New Zealand. It is a pleasure to chat with you again. I really enjoyed my visit in February of this year. So today's topic is prefabrication, installation, testing of geomembranes. Here's the outline of the presentation. I'm going to go very quickly through the first 4 pieces and then focus in on wrinkles and leakage rate calculations. Geomembrane applications. Probably the most common or thought of is waste containment, where we put a barrier layer underneath a landfill or other containment facility to keep the leachate from entering the groundwater system, as you see in this schematic. Once in the groundwater system, the contaminants could reach the surface water bodies and cause further contamination. So get my laser pointer. Here's the surface water location here at the stream. Other applications do not involve hazardous or contaminants. This is a trout farm, fish farm in Michigan, using prefabricated materials in rectangular shapes for a single panel installation using 30 mil or 0.76 millimeter thick PVC geomembrane in a harsh winter climate. Here's a similar trout farm using circular tanks and prefabricated geomembranes installed in one panel very quickly. This is a floating cover system of using the CSPE reinforced geomembrane. The cover system was fabricated in the United States and shipped to Australia and installed in Australia. The advantages, one advantage of prefabrication is the details for the cover system, which are shown on this photograph. For example, you see floats already welded into the cover system right there. And those are done easily in the factory, clean environment, constant temperature, and you can even see a ladder to climb out of the floating cover right there, already prefabricated into the geomembrane. And then the panels unfolded and installed to create the final cover system in Australia. A big use for geomembranes is fresh water, even though most people think of maybe waste containment. But fresh water is very important. The available water in the world is 98% salt water, so we only have 2% fresh water. Of that 2% fresh water, 98% is in ice, 12 in groundwater, and only 1 in rivers and lakes. So we really need to take care of and contain our fresh water to help development and growth in the world. So here's an example of the Columbus, Ohio water reservoir. This is a potable water reservoir, the largest prefabricated geomembrane project in the world. The length is approximately 2 kilometers long, and the width is approximately 1.5 kilometers. The reservoir holds 34 billion liters of fresh water for the city of Columbus, Ohio. Also, potable water, canals to transport the water, because we don't want to lose a lot of the valuable potable water due to leakage out of the canals as it's being transported. And this is an example of geomembranes for not only water containment, but for recreational purposes. This is Prospect Lake in Colorado, where the city of Colorado Springs was spending about $400,000 a year on leakage from the lake, and they had to restore the water at a significant cost to maintain recreational purposes. So the city finally thought to put a geomembrane down, contain the water, and they are saving significant money on water each year. So, geomembrane terminology. There are many types of geomembranes, and this is a sort of glossary of acronyms for different types of geomembranes. I mentioned CSPE earlier, and if you have any questions about the types of geomembranes, they're listed on this slide. Next is chemical resistance. If chemical resistance is not a concern, so in a potable water application, for example, any geomembrane will work. Only when there are significant chemical compounds, which I'll describe in this table here, that you have to think about the selection of the geomembrane. If it's really potable water, the geomembranes will perform well. So let's talk about chemicals. This table rates from A to C. So prolonged contact is A, C is inappropriate use, B is occasional contact. So A, all the materials with A means they can be used for a prolonged time with that compound that's on the left. So the material that really exhibits the best chemical resistance is this EIA. And if I back up one slide, EIA is this ethylene interpolymer alloy material. Let me back up one slide here. EIA. So, depending on the compounds and chemicals you want to contain, you can use a chart like this to pick a suitable geomembrane. Again, if the material that you're containing is not problematically chemically wise, you can use any geomembrane. Okay, market survey. The FGI conducts a market survey annually. This is the 2012 market survey, just to give the viewers an idea of the size of the market. So in Australia and New Zealand, using the metric system, you can see the top table is in square meters. So for unsupported or unreinforced, that's about 50 million square meters. And for supported geomembranes, that's about 164 million, for a total of about 214 million square meters of fabricated geomembranes used in 2012. Okay, leakage calculator. The leakage from a pond or a potable water area can be calculated using Darcy's law, which is the hydraulic conductivity times the gradient times the area of seepage. And the area of seepage is the key. So when we have a potable water reservoir, the area, A, is extremely large. So you get a large leakage just because of the large area, even though the hydraulic conductivity of the subgrade may be small or low. And here are some typical hydraulic conductivities of soils, from gravel to clays, and I'm going to compare that to a geomembrane in just a minute, right here. So the first line is a geosynthetic clay liner, so you can see it has similar hydraulic conductivity to the clay. But now look at the geomembrane. The geomembrane is 2 to 3 orders of magnitude lower than clay. So if you really want to limit leakage from a water containment facility, for example, and maintain that precious fresh water, using a geomembrane is extremely effective. And that's what this pond calculator is going to show in just a minute. This is a cartoon on the right where my pointer is, shows the geomembrane in place, and thus the only way leachate or water can pass into the compacted soil underneath is through that geomembrane, which has an extremely low hydraulic conductivity, versus the left side where it's just compacted soil, and now the leakage is KI times the entire area of the pond. And that's what this spreadsheet can be used for in this slide. So this is called the pond leakage calculator. I'm showing the metric version versus the English version. But you come into the calculator, and this is available on our website, or just email me. I'd be happy to send you the spreadsheet. You put in the dimensions, the top dimensions of the pond, the width, the length, and the depth of the pond. And that gives, the calculator will tell you the total volume of the pond. Then you insert the hydraulic conductivity of the subgrade material, and then the hydraulic conductivity of the geomembrane. And then the calculator will calculate the leakage if you only have compacted soil, and then right below it is if you install a geomembrane. So these two blanks right here give you the importance of installing a geomembrane to reduce the leakage from your pond or waste containment area. Then you can apply the cost of water in your country. In the United States, I use $200,000, it looks like, for 1 hectare per meter of water. And then you can see how much you would save per year by having a geomembrane over just the compacted subgrade. So in this particular case, about $100,000 per year. We also have a panel weight calculator, so you can calculate the weights of these prefabricated panels for shipping purposes. And then we also have a geomembrane leakage calculator, which takes, if there are defects in the geomembrane, you can calculate the leakage through one or more defects. And this is the English version of the pond leakage calculator. Okay, so bottom liner systems. There are a lot of ways we can design bottom liner systems for our containment application. It could simply be a geomembrane over top of prepared subgrade, which is very common for potable water applications. Could be a composite liner system where a geomembrane is placed over a low hydraulic conductivity compacted soil or a geosynthetic clay liner. And then you see the enhanced composite liner system where we put in 2 geomembranes just in case there's a defect in the primary geomembrane. And finally, the double composite liner system, which we use for hazardous materials, where there's a primary geomembrane and a GCL, or compacted soil, a drainage or witness zone, and then the secondary composite liner system with a geomembrane and compacted soil. Here's an example of a double composite liner system, just so you can see the components. From top down, a 30 mil CSPE, a GCL, a geocomposite for the witness zone, another CSPE geomembrane, and a compacted soil liner. And you can see these going in from one end of the pond to the other. What's being installed in this photograph I'm pointing to is the geosynthetic clay liner. In this photograph, you can see a panel of prefabricated geomembrane being unfolded, and then that'll be expanded to cover a significant area, as you see in this low area. And that's really beneficial when we have a GCL, because you want to cover the GCL very quickly such that the bentonite in the GCL doesn't prematurely hydrate. Okay, on to field versus factory fabrication. This is a typical geomembrane installation and assembly in the field. This is challenging because there's the seaming of that geomembrane. You can see dirt and moisture gets into the seam. That all has to be cleaned out before the seam can be welded together for the full length. Then in addition, in the field, if it's a field assembly geomembrane, you must take destructive samples every 150 meters or 500 lineal feet of seam. And those seams have to then be tested to make sure they pass the project specifications. So if you look at this person right here, he's got an armful of destructive samples taken from the production liner, and now, unfortunately, the production liner or geomembrane has to be seamed or patched with an extrusion weld, which I'll talk about next. In factory fabrication, we do not cut destructive samples from the production geomembrane. Trial welds are used instead, so there are no patches in the factory fabricated panels, which I think adds a lot of quality to the final product. I mentioned extrusion welding. So this is the field operation of after you've taken a destructive sample of the seam, you must put a patch over top of it, and generally the only way you can do that for field assembly geomembranes is this extrusion patch. Before you can put the extrudate on, you must use a grinding wheel to remove the waxes that are introduced into the surface of the geomembrane during the manufacturing process so the extrudate sticks. This is some examples of the extrudate coming undone from the geomembrane and causing leakage. It's sort of like a caulk gun if you've used a caulk gun at home. You must get that extrudate to stick to the geomembrane, otherwise the patch will not be effective. Here's an interesting aspect. The extrudate can cause holes in the geomembrane if you leave pieces of it sticking up like you see here. And so that was the extrusion weld on the secondary geomembrane, and when the primary geomembrane was placed over top of it and then loaded, it caused a hole right there where the point is on the extrudate. So raised lumps of extrudate are problematic and need to be removed. Here's some other problems with extrusion welds, wrinkles, and so on. Okay, Brian Queen of the Ohio EPA put together some statistics about leakage from waste containment facilities. And generally, his data shows about one hole per 5 acres. Of those holes, 10% were due to extrusion welds, 15% just due to field welding, dirt in the seams, as I talked about earlier, and about 75% of the holes was due to soil cover placement. Prefabricated panels can be created in the factory and then shipped to the field, and a panel layout diagram, as you see here for an MSW landfill, can be created, and the panels are numbered. They are shipped to the right spot on the diagram, unfolded, and this is a way to quickly install a significant amount of geomembrane and also minimize the amount of field seams that have to be undertaken. That panel diagram that I'm pointing to is this MSW landfill you see in the bottom photograph, and there's one of the panels being unfolded and installed. Here's the factory fabrication: clean setting, constant temperature, hard subgrade, very easy to weld seams in a factory versus what you see in the field. This is a photo from the site that I showed earlier. Here's another factory fabrication operation. Very large quantities of geomembrane can be seamed, folded, and ready for shipment. All times of the year, year-round. This is a year-round operation in the factory. Okay, frequency of seam testing for factory fabricated panels. No destructive seam test. Only tests on trial seams by each machine and operator combo at the beginning of the shift, every 4 hours, and at the end of the shift to make sure the settings and operation are still producing good seams. So there is no destructive sample taken from the production geomembrane. Fabricators also test individual geomembranes as part of the CQA process. Destructive seam testing on those trial welds can be performed using these various ASTM tests: solvent welds, for unreinforced materials, tape seams, and reinforced materials. These ASTM test methods can be used. For panel handling, storage, and deployment, use ASTM D7865. This shows you how to identify the panels, unroll them, unfold them, package them, transport them, and then deploy them at the field site. Here are some photographs showing the panels being folded up in accordion fold in the upper two photographs, or they can be rolled up in rolls like you see in the bottom photograph that I'm pointing to. Either way, they're put on flatbed trucks usually and shipped to the site. The only thing limiting the size of the panels is the shipping weight in that particular truckload to the site. Once they're at the site, those panels can be unfolded, as you see in this upper photograph, pulled out, and then a little air underneath the panel, and they slide right into place, as you see right here. This photograph I'm pointing to in the lower right, look how nice it's laying in on the subgrade. Very little wrinkles with these prefabricated materials, and I'm going to talk about that a lot in just a minute once the panel's in place and stretched out. Complicated geometries can be prefabricated in the factory, as you see in this photograph. This is actually a folded up circular geomembrane for a large tank for a shale oil and gas operation. That'll unfold into a very large circle. Other complex geometries, such as those shown here, can be prefabricated and then just unfolded in the field. The bottom one is a tank pad liner. As you can see, it's already prefabbed as a circle, ready for the tank to be placed on top. Here is a water canal with a bend in it and prefabricated materials already being fit and sized for that bend instead of trying to cut and form it up in the field. In this particular case, the prefabricated panels are shipped rolled up instead of accordion folded. Okay, we're on to installation. There are some installation guidelines that we created with the IAGI group, the International Association of Geosynthetic Installers, IAGI. We developed 3 installation guidelines with IAGI for lightweight reinforced geomembranes, heavyweight reinforced geomembranes, and unreinforced geomembranes. These installation guidelines are available on the FGI website as well as the IAGI website, and they are free. I urge you to download those and learn more about how easily these panels can be installed. Here's a comparison between field assembly and factory fabrication. The upper panel or roll layout is for a landfill cover 9.3 hectares in size. It would take 13,725 meters of field seams to seam all those rolls together. About 75 hours of welding, 25 days for installation, and they could install about 3,700 square meters per day for field assembly. Versus the panel diagram shown in the bottom, same landfill cover. The panels would be 91 meters by 21 meters and only 5,000 meters of field seams being required. So only about 20 hours of field welding, 10 days for installation, and installing about 9,300 square meters per day because you're installing panels and welding less in the field. In addition, that would require much less CQA time in the field because the operation only requires 10 days of installation, not 25. So this gives an idea of the comparison for a different landfill cover. This would be 93, actually, no, maybe it's This would require 23 panels, factory assembly. The field length of seams would be about 4,700 meters. And if it was field assembled, there would be 29 rolls of geomembrane, and that would require about 15,000 meters, linear meters of field welding to complete this landfill cover. So 3 times as much field seaming with field assembly. And of course, that means more time, more destructive testing, more CQA as well. And I don't have time to talk about the Columbus Reservoir, but that project showed that the factory welded seams were of higher quality than the field assembly, with the shear and peel of the seams being about 10% stronger in the factory than the field. Okay, so here's a cost breakdown for that landfill cover that I just mentioned, the 23 panels and versus the 29 rolls. So notice the destructive tests, 30 tests for the field assembly. You can multiply that by $30 per test and get a cost. And third-party CQA is $9,000. So roughly for the factory assembly geomembrane, you have a installation cost and CQA of about $10,000. Compare that with the field assembly, where now you have 95 tests, 15 days of assembly in the field. So that total is about 25,000 versus 10,000. So about 2.5 times more CQA cost for field assembly versus factory assembly. As I mentioned, the only thing limiting the size of the panel is the shipping weight. And so you can use our panel weight calculator to estimate the weight of the panels and then the panel size for your particular truck load limit you can ship. So you use the weight of the geomembranes, which is in this column in kPa or kilopascals, for LLPE down to reinforced polypropylene. And you take the panel area, you multiply that by the weight per area, and that can be used to estimate the panel dimension for a particular shipping weight. In this particular case, I used 2,700 kilograms, which is 6,000 pounds in English units. So these panel dimensions that you see on the right, 46 meters by 63 meters, corresponds to 2,700 kilograms or 6,000 pounds, which is a typical shipping weight in the United States. Here is the weight per area for those same geomembranes in pounds per square foot for the US audience. So field non-destructive tests for factory fabricated panels. You can air channel test it using ASTM D4437. You can also run seam integrity tests using the air lance under 4437, vacuum chamber boxes, and spark testing. But the most common is the air lance test, which I'll show you in just a minute. It's very quick, and you run it along the seams. Here's the air lance under 4437. A pressurized nozzle is run along the side of the seam, and if you hear changes in the air, there could be a leak there, so you need to check it. Also used in the factory. Here's air channel testing. This has been a really important development for factory fabricated materials because generally they're more flexible. And so when you inflate the air channel, you can actually see it inflated. So not only do you measure the pressure in the channel, you can also visually check the channel to make sure it doesn't have any aneurysms or weak spots in it, which I'll show you on the next photograph. This is like pumping up your bicycle tube, and you can see if there are any defects in the seam. I think it's a very powerful, not only quantitative, but qualitative assessment of the seam. Here's an example of an aneurysm in a factory fabricated geomembrane. So there must have been some dirt or maybe moisture in the seam, so the weld was not as wide in this location where the aneurysm is as it is over here. So the aneurysm was able to move out further than the tight little air channel that you see left and right of the aneurysm. Okay, that brings me to wrinkles and leakage rate. Wrinkles, very important topic right now because we can get leakage around wrinkles. So if my geomembrane happens to have a defect, as you see on the right here, instead of an intact geomembrane, we can get leakage through that hole. And the whole point of having a compacted low hydraulic conductivity layer underneath the geomembrane is that if there is a defect, that the area of seepage is only the area of the defect. So if I go back to the cartoon on the left, the area of seepage is the entire pond area because there's no geomembrane here. Okay, so if I have a geomembrane and it has a defect, if there is intimate contact between the geomembrane and the compacted soil underneath, the leakage is controlled by the area of the defect. Now, if there is not, that area becomes much larger. And I'm going to illustrate that with J.P. Giroux's 2017 expression for leakage rate through a hole in the geomembrane from his 5th de Mello lecture in Brazil. This is his expression. You can use the hole area, a hole diameter. You pick the number of holes per hectare, and you can estimate the leakage rate with intimate contact, and it ranges from about 1.3 to 1.6 liters per hectare per day. Now, remember 1.3 to 1.6, because now I'm going to compare that to what happens if we have a wrinkle, because then there's not intimate contact. So, factory fabricated materials are generally more flexible, have a lower Young's modulus, and a higher interface strength, and thus lay flatter, and if there are wrinkles, they're much smaller and not connected, as I'm going to illustrate in these couple of photographs. This is a high-density polyethylene geomembrane from Giroux and Wallace. Look at all the wrinkles. These are not only causing non-intimate contact, but now these wrinkles are all interconnected, so moisture can get underneath a significant area of this geomembrane, and your area of seepage is much bigger than just the defect. So the Ohio EPA developed statistics for HDPE wrinkles. They range from about 0.18 to 0.23 meters tall, 7 to 9 inches, and they're about 3 to 6 meters apart. Leakage, when we have non-intimate contact, is generally 100 to 1,000 times greater than calculated using J.P. Giroux's expression that I just mentioned. So there's additional moisture getting below the geomembrane and the larger area of seepage causing significantly greater leakage. In addition, these wrinkles can impede flow to the sump, and thus heads can build up on top of the geomembrane, allowing additional liquid to get underneath the geomembrane. Prefabricated geomembranes in the factory, Ohio EPA statistics show the wrinkles are about 25 to 50 millimeters high, only about 1 inch to 2 inch versus 7 to 9 inches for field assembly geomembranes. And the geomembrane wrinkles in prefabricated materials are much closer together, so smaller, closer together, say 0.3 to 0.6 meters, not interconnected. For example, look at this photograph of a factory fabricated panel geomembrane installation very flat, and that's a good example of intimate contact. Even LLDPE is sort of in between the factory materials and high-density polyethylene, using Ohio EPA statistics, wrinkles heights of 75 to 125 millimeters, and the wrinkles being a little further apart, like you see in the photograph below, say 0.9 to 1.5 meters apart. So why is this important? Song and Kerner in 1998, as well as excavation of several facilities after a slope failure, show these wrinkles do not disappear even though the facility is filled with waste above it. So there's always a void below the wrinkle that allows seepage and liquid migration, and thus a larger seepage area than just the defect. Kerry Rowe at Queen's University has a field test that shows typical widths of wrinkles 0.2 to 0.3 meters, wrinkle heights 0.06 to 0.2. The wrinkle area can be as much as 30% of the lined area, and wrinkle length is typically about 200 meters long. So you have a significant area of seepage below the wrinkles. Okay, so let's look at leakage rate with wrinkles. Okay, so I just want to point out that the area of seepage with intimate contact is the defect, but when we have a wrinkle, it's much greater than the defect. So Kerry Rowe has developed a similar expression to J.P. Giroux's expression for leakage when we have a wrinkle. L and B denote the geometry of the wrinkle, and theta is the transmissivity between the geomembrane wrinkle and the subgrade. Using that expression, here's a similar table of calculations to what I showed from using J.P. Giroux's equation. And with one hole and intimate contact, remember I gave you a value of about 1.5 liters per hectare per day. You can see that with wrinkles, the leakage rate is 100 times that of intimate contact. And field observations from the Ohio EPA say that that leakage rate with wrinkles can be from 100 to 1,000 times greater than what we calculate with this expression. So I think that's due to the larger seepage area underneath the wrinkles and the interconnectedness of the wrinkles. So let me quickly talk about action leakage rate in my last couple of minutes. This is a difficult problem. So what is the action leakage rate? When do we have to impose a repair if leakage appears in our witness zone? So US EPA has some guidance from 1992. If there's 1 foot ahead, the leakage rate could be 935 liters per hectare per day, with a higher hydraulic head up, say, 10 times that. State regulators have other values. I put in New York here, for example, so you can look at those. But what I'd like to leave you with is that there is always a lower bound of leakage, because even if the geomembrane is intact, no defects, we still get some vapor transmission through a geomembrane. So it cannot be zero, Even if the geomembrane doesn't have a defect, if sufficient time is allowed, there will be some vapor transmission through an intact geomembrane. You can see the migration coefficient is extremely low, 10 to the negative 16 meters squared per second, but there is some small de minimis amount, so not zero. Okay, so effective wrinkles, to summarize: with wrinkles, we don't have intimate contact. The leakage rate will be 100 to 1,000 times greater than that calculated for a intimate contact situation. The wrinkles cause localized stresses and strains, and those stresses and strains can cause cracks and stress cracks in field assembled geomembranes. They can also interfere with drainage above the geomembrane, cause bentonite migration in the GCL below it, and also increase the potential for construction damage because things get stuck or caught on wrinkles. Finally, wrinkles are difficult and impede the performance of leak location surveys, which is gaining a lot of attention in the United States because some states are now requiring leak location surveys. Okay, to wrap up, CMAC, quick summary, prefabrication, the geomembranes are seamed in a controlled environment. We can create large panels and ship those. The only limit in size is really shipping weight. That can lead to 80% less field seams, so that's quicker installation, especially in harsh weather areas or where the construction season might be limited. Many geomembranes can be installed in a single piece, especially tank liners. The only limiting factor is shipping weight. And during installation of these prefabricated panels, we do not take any destructive seam test. We use non-destructive air channel testing or air lance testing. There'll be fewer wrinkles and smaller wrinkles, and because of that, all leak location methods are able to be used with factory fabricated panels. So, CMAC, let's see if we can try to answer some questions. Yep, and I can send it to you, and I think maybe I have already, but I'll send it to you. CSP is a geomembrane that has been around a really long time. It's chlorosulfonated polyethylene, and actually maybe I can go back there, but CSPE still used a lot, maybe not as much as maybe 10 years ago or so, but a very durable, good geomembrane. And it can be factory fabricated, panelized, and shipped to a site, no problem. There's only one geomembrane that cannot be factory fabricated, and that's HDPE. Because when you fold it, it creases. It's too stiff. So LLDPE, any other EIAs, PVC, polypropylene, everything else can be factory fabricated. No, because those other geomembranes that I mentioned are amorphous or non-crystalline. So they do not crease or cause creasing and stress cracking problems. It's only the crystalline geomembrane, which I already mentioned, there's only one of them, that these creases cause a stress crack location. Oh, that's a great question. So ideally, the material shouldn't be allowed to freeze, although it will thaw out eventually, but in general, it's best not to have it freeze. Um, like you said, in a enclosed environment is better, so it's not exposed to the weather and the elements. But all of the ship panels are pre-wrapped, as you saw in some of the photos. There's always a plastic wrapping around it, so that keeps a lot of the dirt out. But it's best for it to be enclosed in a building and not to freeze. The ASTM guideline that I mentioned on handling, shipping, and deployment gives recommendations for how to store the material as well.
There are a couple of questions about the panels being prefabricated and during the shipping or when they're in the cabin, getting scratches or pinches when folded during the transport.
So if it is accordion folded, as you saw in some of the photos, there's a wooden pallet that's underneath the panel. And so the forklifts only lift and move the panel through that wooden pallet, and that prevents any damage to the geomembrane. If it's rolled up on a roll, as you saw in a couple cases, a rod is placed down the core and it is lifted through the rod. So that's the way to prevent damage to the panels in the field.
Another quick one about because they're heavier when they're prefabricated and shipped to the site, is it more difficult for field personnel to unroll?
No, because the accordion, literally, if it's at the top of the slope, you can pull it down the slope and it accordion unfolds right down the slope. Or you saw in a couple photographs, it was on a forklift and the forklift just backs up the slope and somebody just holds the end and it unfolds from the accordion stack. Of course, from the roll, you can just pull off the panel and then you unfold it and then spread it out in the field. So either way, it's a pretty easy process.
And again, in line with that, difference between or the benefits of having a screen reinforced versus unreinforced, because we have examples of durability failures on the fold lines. That is the question.
Okay, and are the fold lines, they're seeing that with reinforced or unreinforced or both, I guess?
Maybe both, I think.
So I would not anticipate fold lines.
Sorry, reinforced, they say.
Oh, reinforced. Must have been a thicker geomembrane because generally the reinforcing scrim actually helps hold it together. So I'm a little puzzled by that. I'm going to make a note. It would be great if that person could email me and I will try to give them some better information, but I have not heard about a reinforced panel having a crease in it.
Yep, the person says he's got your email address. He will email you.
Great, thank you.
That's all the questions that we have time for. So I'm now making Jashwin a panelist, and then he will present to us the FabTech presentation.
Great.
Thank you, Tim.
Thank you.
Jashwin, you're mute now. Yeah, Tim, you just need to stop sharing.
Okay. I don't see that button.
If you scroll right to the top of the screen, that will pop down.
New share.